Welcome to qnawire.
So to find the angular momentum, we will use equation 11.1. It says that L is given by I, which is moment of inertia, times omega, which is uh, the angular velocity in terms of radians per second. And here I is half mr square. Now we will use these values into this equation. So we have half times the mass times radius. So I wrote here small r, so these are basically the same. So this is equal to 0.18 meter square, and omega is given in terms of in units of revolutions per minute. So we have to convert it into radians per second now. So we know that one revolution is 2 pi radian. So 1300 revolutions will cover an angle of 2 pi times 1300 radians, and this is in units of revolutions per minute. So we have to convert this minute into seconds, and we know that 1 minute is 60 seconds. So there we have our omega in terms of in units of radians per second. Now we solve this equation and we get L to be 6.175 kg meter square per second. So this is the first part. For the second part, we have to find the torque. We know that torque is change in angular momentum per unit time. So mathematically, we can write it to be LF minus LI, which is del L, or change in angular momentum, over unit time, which is delta T now. And the final angular momentum is 0, so LF is 0. Initial angular momentum is the one that we calculated in part A. So we use that over here, and time is 6 seconds. So we solve this equation and we get torque to be equal to kg meter square, and in units of Newton, this is equal to 1.0 Newton times meter. The negative sign indicates that the torque is used to oppose the initial angular momentum. And this makes sense because the final angular momentum is 0. Therefore, there need to be a negative torque applied to decrease the angular momentum to 0. This is analogous to applying a negative acceleration or deceleration when you are trying to slow down a particle, and the final velocity is 0 or less than the initial velocity.